This presentation is entitled Soft Star Schema Data Warehouse. Now you might have heard of a star schema data warehouse. This particular presentation introduces a new concept, the notion of something called a soft schema, utilized in support of data warehouse technology. In this presentation, we talk about the difference between data versus information versus knowledge. Now today, we live in an era of information systems. And what is described in this presentation is a way of morphing information systems into what are called knowledge management systems.
Soft Star Schema Data Warehouse. Information technology has a number of challenges associated with it today. In today's presentation, we're going to look at three. We're going to look at something called a fragility problem. Oftentimes in software architecture, an architecture is broken down into a number of tiers. And the fragility problem is one where you make changes in one of the tiers and you get this ripple effect that causes breakage in other layers. Second problem is one of rigidity. It's the inability to easily modify data schemas on the fly. The third challenge is one of complexity. Oftentimes an enterprise system contains potentially tens of thousands of underlying database tables. There are a number of steps associated with providing general query capability on structured data. In today's presentation, we're going to look at two steps that address the problems identified on the previous slide. We're going to look at creating a simplified data warehouse and mapping data from your enterprise system into this data warehouse. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here, and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph, and assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. Let's look at the difference between data versus information versus knowledge. If I showed you the following, would you consider this to be data or information or knowledge? Well, it turns out it's just data. And the reason why is because you look at this and it looks like a column of names. That's because it is something you recognize. This looks like a column of diseases. That's because you're familiar with it. But by itself, it is merely data, just text strings. Now, if I add column headers here, these column headers are what are known as metadata. And so what we get is data here plus metadata is our definition of information. Well, what if I take and put an overlay here, the following? We see type 1 and type 2 diabetes are specializations of this more general category of diabetes. Ulcerative colitis and Crohn's disease are specializations of this more general category called digestive diseases. So what do you call this structure here, this knowledge overlay? I call it meta-information. And so my definition of knowledge is information plus meta-information. This knowledge overlay here is something called an ontology here. There are semantic relationships between the nodes here. And what this allows you to do is the following. If you view this as a relational table here, you can certainly ask questions about who has type 1 diabetes in your database here. What an ontology overlay allows you to do is ask higher level questions. Tell me all the people in my system that have diabetes in general or have autoimmune diseases in general. In the previous slide, we talked about the difference between data versus information versus knowledge. And I pointed out the value in taking an information system and overlaying it with a knowledge layer here. So what we're going to look at here is an architecture to in fact do exactly that. Take an information system and transform it into a knowledge system, which is a data warehouse plus an ontology layer here. In previous slides, we talked about the fact that ontologies can be represented as a graph, and we talked about the notion of a soft schema, 6 relational tables to represent graphs here. So I'm going to initially focus on looking at the internals of a data warehouse. Let's look at a classic star schema data warehouse, which has the notion of a fact table. A fact table has columns consisting of dimensions, where each dimension here is a table of flat records here. A characteristic of this approach is that there are a fixed finite number of dimensions associated with a fact record. Also to point out that these dimension tables, they're just flat lists. There's no semantic relationship associated with any records between dimensions. In this slide here, we've taken our classic star schema data warehouse shown on the previous slide, and we've performed a transformation. In particular, we've replaced the dimension tables here with ontologies here. So now all of the dimension columns here are pointing to nodes in ontologies. And so we still have a fixed number of dimensions in our fact table here. And as I mentioned, now the dimension tables are ontology nodes here. In this slide, we have taken the data warehouse shown in the previous slide and performed yet another transformation. In this case, we've taken our fact table and have performed a pivot. So now each row in the fact table points to nodes in ontologies here. So what this allows is the ability to have a flexible number of dimensions here. So if we add a new ontology here in a new dimension, we simply add new rows to the fact table. Given the transformations I just described, Let's now look at a knowledge system schema that pulls it all together here. So for our data warehouse, I'm proposing 4 tables here. So here's our fact table here, and it's a pivoted fact table here. So we have 1 row for each dimension, and our dimensions really are pointers to ontology nodes here. And every fact record has a context of an event. So we have an event ID here in the context of an entity. So we have an entity ID here. And we have a fact extension table here. So think of this as a star schema snowflake kind of model here. Here's our knowledge layer, and it's comprised of 6 soft schema tables that I talked about previously here. And so you'll notice here's our object table, and it has an object ID here. And so this represents nodes in your ontology here. And as you can see here, our fact table, every row points to a node in our ontology. Okay, here's our knowledge system architecture picture again. We just got done looking at the internals of these 2 components here. One of the problems with this architecture is this guy right here, custom ETL. For every different kind of information system, we have to write custom ETL to pull the data from the information system into our data warehouse tables. The following is a proposal for an alternative database schema, one that uses a soft star schema for both the knowledge layer and the data warehouse. And we've, instead of simply our 6 soft schema tables, we've added a couple other tables. We have here a namespace table, which represents a collection of classes, and a vocabulary table representing a collection of objects here. And we'll see in a minute how this particular schema solves the custom ETL problem. Okay, so here's our business enterprise system again, and we show XML data being pulled into our information system. One of the things I've mentioned in a previous presentation is TCSQL's ability to read in any XML data into something called a soft schema. Okay, so with that in mind, and looking at the previous slide here, we're going to use our soft schema here to pull in XML here that would normally simply go straight into an information system. In this case, we have a generalized ETL process here. So we're going to use a soft schema here for the data warehouse, and we're also going to use that same soft schema to represent our ontologies here. And so now the advantage of this architecture, this alternative, is the following. First of all, we no longer require access directly to the information system here. Secondly, as I've already pointed out, we're able to pull in XML directly into our soft schema data warehouse here. And more importantly, with this very generalized data schema here, we now have the ability to write very generalized, very powerful SQL queries that are heterogeneous, that can cross different kinds of XML documents. So, in summary, what is the value of all of this? And again, it is the following. I've demonstrated the ability to import new XML documents without having to make any ETL changes. It's generalized ETL. And secondly, as I alluded to in the last slide, the ability to write generalized queries that are heterogeneous, that can be applied to any XML document without having to make any query definition changes.